Well, everybody, I think we all knew this day was going to come. We've been talking about all these analogs between rotation and translational motion. We talked about angular acceleration and how it's like linear acceleration, but for rotational motion. We talked about torque and how it's something that changes rotational motion, like force changes linear motion or translational motion. We even talked about moment of inertia or rotational inertia. Now that's a resistance to change in rotation, kind of like mass is a resistance to change in translational motion. Now it's time to put all three of those together. Newton's second law for rotation. Now the great thing about this is that it is such a close analogy between translational motion and rotational motion that a lot of this will seem very familiar. So we've kind of got our ducks all in a row here. Now we can move on. So this should be a vector, as should this. We can kind of move on to the second law stuff. Acceleration in linear motion we said was net force divided by the mass. Now we're on to linear acceleration. It's going to be equal to the net torque divided by the rotational inertia. And there we have it, second law for rotational motion. For our first example with this, let's look at baton twirling, a subject I am going to pretend I know something about. So, we've got mass and we've got force given to us here. In the old days, we'd be set. Mass and force, plug those into Newton's second law and we're done. Well, we got a little more work when it's angular acceleration we're looking for. Angular acceleration, remember, is equal to the net torque divided by the rotational inertia. Now, we don't have values for torque or for rotational inertia, so we got a little work to do before we can get either of those. Once we have those, it's pretty easy to plug those in and find the angular acceleration. So let's visualize this. So we've got our baton here, and it says it's light except for the weighted ends. The weighted ends are 0.50 kilograms. The whole thing is 1.0 meters long. And then we've got some center point here as well. Now let's say we're applying one force this way and one force this way. Doesn't really specify, so I probably should have been a little clearer with the wording, but we're trying to make the thing twirl, so we're going to apply forces in opposite directions. And those are 5 centimeters from the center of the stick. Let's do rotational inertia first. So rotational inertia is equal to the summation of mr squared for each of these masses. So we've got 2 of them, and they're both the same distance apart here, so this will be pretty straightforward. We're going to rotate it around the middle of that middle point here. So our mass for each one of these is 0.50 kilograms, and the distance for each one is going to be 0.50 meters from the center, from our axis of rotation, and that gets squared. And there's just 2 exactly like this, so I'm just going to multiply by 2. And so that's going to give us 0.25 times 0.5 times 2 again is just going to be 0.25 kilogram meters squared. Alright, so we're halfway there. Now we need to figure out torque, the net torque in fact. So that's just going to be our forces times their distance from the axis of rotation. So again, we've got 2 identical forces, so it's Fr sine theta, and we'll do that twice. So we've got 2 identical forces here. Those 2 forces are 25 newtons. They are 0.05 meters from the center. Sine of 90 times 2. Alright, so 2 times the 0.05 is 0.5, so this is going to be 12.5 Newton meters. And by convention, torques that cause a clockwise rotation we're going to write as as negative torques. Counterclockwise goes with positive. This one calls them makes this thing rotate counterclockwise, so we'll have positive torques here. So then our angular acceleration. Angular acceleration is going to be equal to the net torque divided by the rotational inertia, so 12.5 Newton meters divided by 0.25 kilogram meters squared, and we end up with here, divided by 1/4, so times 4, that'd be 2550. And the units on angular acceleration are radians per second squared. It's worth noting here that the radians actually you kind of have to just write in. If you do the units on this, remember newtons is an abbreviated unit. So let's look at that briefly. Newtons means kilogram meter per second squared times meters divided by kilogram meters squared. So we've got meters squared on bottom and 2 factors of meter on top. Kilogram on the bottom, kilogram on top. You end up just with 1/seconds squared. So radians is one that we kind of write in here when we're solving these ones. It does work out, but the units won't appear in the other units that we do in the calculations. So just be aware of that we do need to write in the radians per second squared. Anyway, 50 radians per second squared for this. If we move those masses out a little further or made them more massive, we'd have a greater rotational inertia, so this alpha number would decrease. If we had bigger forces or moved the forces out from the center a little bit, then we'd have more torque, and so this angular acceleration would increase in that case. So it's a fairly straightforward process when you have simple forces. It just gets more complicated if we have different shapes, and especially when we get to linear motion and rotational motion at the same time, like something rolling down a hill, for example. So, more on that to come. If you found this video useful, please go ahead and like it so it's easier for other people to find and use as a resource as well. Feel free to subscribe as well. I put out videos a couple of times a week usually, and if you liked this one, why not the other ones? Thanks for watching, everybody.